Okay. Well, today we're very happy to have Dan Hackett, who came to visit us from Fermilab, where he's doing his postdoc since September. And before that, he was at MIT as a postdoc, and before that, he was a PhD student of Ethan Niels and Tom DeGrantz at Boulder, Colorado. And he has worked on a gigantic variety of different topics in lattice QCD and beyond. And today, he will talk to us specifically about his work that he's been doing regarding machine learned flows for QCD. And take it away, Dan.
Cool. Yeah, so thanks everyone for coming. Thanks to the organizers for inviting me. I've always wanted to come here, so it's nice to finally get to visit. Yeah, so I'm going to tell you about some work I've been doing in collaboration with quite a few people over what's approaching now half a decade. So here's pictures of lots of them. You'll notice that one of them, Tej, is right there. So he will, of course, be judging my presentation. He's done a lot of the work on this, but also all of these people as well. And assuming I make it to the end of my talk, I'll be showing you especially a lot of work that I did in close collaboration with that guy, Ramiro Lopez, who you may recall was here until yesterday. Okay, so let's start with sort of what I always think is kind of the elephant in the room when you're talking about machine learning, which is that neural networks are kind of black boxes. They're not really like kind of black boxes, they're actually black boxes in a meaningful sense. So let's dig into that idea. So the idea, all of machine learning, I think you can summarize by this thing, where if I have some untrained neural network, some parameterization of some function, and I have some cleverly engineered training procedure, I can tune that neural network to approximate some function with some properties I might find to be useful. So, you know, for some, if we're trying to do physics with machine learning, so we have some function we want to approximate in our analysis or calculation or whatever, machine learning methods can often provide a useful high-quality approximation. So useful kind of depends on the context. The important thing to note, though, is that this kind of, this approximation is uncontrolled. There's no sense in which you can really systematically improve a learned function in this way, or like rigorously bound its errors. You always end up having some sort of irreducible model uncertainty when you do these things. And so that's the sense in which they're black boxes. And it sort of raises the question, like if we're doing theoretical physics, if we really need to rigorously say what something is or isn't, say what the value of something is, we need some way of sort of, you know, how can we use something with irreducible model uncertainties to do that? And specifically, how can we do this for lattice QCD? So that's sort of what I'll set out to talk about. So here's an overview of my talk from here on out. So first, I'll review what is lattice quantum field theory, or lattice quantum chromodynamics, in case you're not familiar. Then I'll talk a little bit about generative models for quantum field theories and flows in general, sort of review the concepts of that we'll need to understand to get to the next part, which is how we've been building flows to do lattice QCD problems. And then finally, towards the end, assuming I don't completely run out of time, I'll talk about some more recent work we've been doing to use shorter flows to maybe get some useful sampling or computational advantages while we're still working on making flows of higher quality. Yeah.
May I ask a short question?
Yeah, go for it.
So for the function fx, can I have a classical function, but the output actually gives me a quantum effect, which there's some random quantum effect as the output?
There's an entire field called quantum machine learning, which I assume addresses that, but I've never thought about that before.
So, but in this one, we are just...
Yeah, we're just thinking about classical computing, no quantum computing.
Okay.
Yeah, good. Yeah, I guess the other thing is, okay, so if you don't care about lattice QCD and you don't care about how we do sampling in lattice QCD in particular, you might be worried this talk is not going to be boring, but I hope it won't be. I think a lot of the concepts buried in this are very physical feeling. And beyond that, I think some of the machine learning technology I'm going to talk about is very useful for other problems than just lattice QCD. So I'm hoping that you'll at least take that much out of it. Okay, so first, what is lattice QCD? So I probably don't need to introduce quantum chromodynamics to this audience, but it's the QFT that describes the strong force, but you can't really do perturbation theory if you want to learn about QCD in the world around us. It'll work at high energies and tell you something about colliders, but if you really want to learn about QCD, you're going to need to do something else. And the main something else is lattice QCD, where we discretize the QCD path integral and evaluate it using Markov-Chain Monte Carlo methods. So this is an integral part of the nuclear particle theory toolkit. Some recent highlights are, I think it's fair to say that, maybe this is speculative, but I think lattice kind of just saved us from claiming a false discovery on mu on G-2. Also note that there's been some really interesting recent work on gravitational form factors that have come up, and I think are particularly cool. Okay, so yeah, so lattice QCD, what is lattice QCD? It's just doing integrals, it's just doing path integrals. So the setup is this. So we take our 3 + 1 dimensional quantum field theory, we whip rotate, and we get 4-dimensional static. We restrict to a finite volume because you can't fit an infinite volume on a computer. You also discretize space-time because you can't fit a continuum on a computer. The result looks something like this. So your degrees of freedom are laid out on this lattice, where each site is connected by links. And I'll say a little more about that on the next slide. So now, if I do this, I take my infinite dimensional path integral and I convert it to a multi-dimensional integral that I can just do on a computer. And so what computing an expectation looks like in this context is this. So I have some QFT expectation in Euclidean time, then I'll just have some action that instead of e to the is, as long as my action is real, it'll look like e to the minus s. Everything in here is discretized, and this is some observable I'd like to compute. So this factor, 1 over z e to the minus s, where z is the partition function, this is just something you can interpret as a probability density. So I can rewrite this quantum field theory integral as just some statistical expectation integral. I can sample that using Markov-Chain Monte Carlo methods. So this is some density over the space of field configurations. And I can use existing algorithms that people have been designing and iterating on for decades to draw samples from this distribution. Once I do that, I can compute an expectation value just by evaluating the observable on each configuration and taking an average. So standard Monte Carlo picture. So this lets us do numerical quantum field theory. That's the setup. A little more on what the degrees of freedom look like. So lattice gauge fields, you have gauge fields living on the link. And so these are sort of parallel transporters that carry around your color degrees of freedom, let's say. So for photons, each link is a phase valued thing. For gluons, each phase is a SU3 matrix valued thing. Matter fields live on the sites. So on each site, you might have a real or complex number if you had scalar degrees of freedom, which we don't in QCD. We have fermions, so instead we put down Grassmann variables on each site. And we usually integrate those out analytically. So numerically, what we're dealing with are just the gauge lengths. So the integrals for these are very high dimensional. And I think there's a real sense in which these are sort of the highest dimensional integrals that anyone does exactly. So here's an example from a calculation I was involved in with Dimitra recently, where we computed the gravitational form factors of the proton and pion. And in this calculation, just to give you an idea of the integral dimensionality, the lattices we were using were 48 cubed by 96 sites. On each site, you have 4 gauge links, and in each link, you have 8 independent degrees of freedom, kind of depending on how you want to count them. So you end up with almost 1 billion dimensions. And this is the dimension of the integral we're doing in order to compute these quantities. So, and similarly, this is the dimension of the sampling problem we'll have to do using Monte Carlo methods. So this is sort of enormous compared to most other numerical sampling problems. Give you a little more idea of what lattice QCD looks like calculationally, what the workflow is. So there's sort of 3 main stages if you want to chop it up like this. The first one is the sampling problem I've already been referring to. So we generate ensembles of gauge configurations for different discretized versions of QCD. And so this is just sampling from that density I wrote down earlier. Then, given these ensembles, we can evaluate observables on each configuration U and use that to compute expectations using just Monte Carlo, like I said earlier. So these are asymptotically unbiased estimators. So we're guaranteed to get exact results for our theories as long as we do the sampling problem correctly. Given that, we can then analyze these correlation functions we've computed to extract physics. So things like masses, matrix elements, tedronic properties, that sorts of thing, anything you might care about getting out of QCD. And by repeating this at various different lattice spacings, we can extrapolate to the continuum limit where universality guarantees will get the same value that shows up in real-world QCD. Okay, yeah, so there's lots of work being done and has been being done for several years. We have this nice snowmass white paper where we summarized a bunch of it. But I just want to focus now on specifically these two parts of the calculation are where most of the computational expense is. This part, there's lots of work that goes into it, a lot of formalism, but computationally, it's usually not as bad in terms of flops necessary. So the question is, can we accelerate these two stages, and especially this first stage, using machine learning? Okay, so a little more on this first bit, the sampling problem. So what does it look like when you do sampling with Markov chain Monte Carlo? So suppose this is sort of the potential surface described by our action. So here we have some region of low action where we expect our theory to be more heavily weighted. We expect, this is configuration space. We expect this part of this region of higher density to dominate the integral. But we also know that we're going to take a flat average. So we expect this region will get sampled more. And so the way MCMC algorithms work is, if you remember your undergrad thermodynamics, you have this whole picture of the ergodic theorem where time averages are equivalent to ensemble averages if you have ergodic dynamics. And that's indeed exactly how Markov chain Monte Carlo algorithms work. You set up some time evolution of a process that will guarantee you spend the appropriate amount of time in each part of your potential. So what that looks like is this. So imagine you have some system state and you're evolving, and each one of these points is a sample you've drawn. And so if your system keeps evolving around in your potential, you'll spend more time around these regions of high potential, occasionally end up in regions of low density. And by following this trajectory, averaging along it, this is how you sort of get the correct expectations. The standard algorithm we use to do this for QCD is something called hybrid or Hamiltonian Monte Carlo, which maybe you've heard of. Okay, so the main sampling problem we'd like to beat is something called topological freezing. So this is a problem that's sort of specific to QCD as described here, but an example of a much more general problem, which is that the gauge field distribution is multimodal. What that means, or in this case, what that means is there are different, you can divide the set of all possible gauge configurations based off what their topological charge is. So just the integral of FF dual. And when you're trying to sample from the theory, you find that there are sort of large potential barriers between configurations of different topological charge. So as you're sampling, you must sort of sample over all of these different topological sectors to get your physics correct. But that requires that, imagine you're bouncing around over in this mode. You notice there's like a region of low density here connecting the two modes. So only very rarely will you have some event that tunnels you from one mode to the next, so you can start sampling this one. And you need to see very many of these in order to get the correct relative mode weightings to get any averages correct. And in fact, as you try and take the continuum limit, the rate at which you tunnel between these sectors, the separation between the modes, becomes exponentially severe. So this can result in an effective loss of ergodicity. Like I mentioned earlier, we really need ergodic exploration in order to get our expectation values right. This can do things like give you apparent convergence to wrong answers at any sample size you might be able to actually achieve. So just to give you an example of kind of what this looks like in practice, in practice you usually know when this is happening. You can measure the topological charge and check that it's not frozen. So there's unlikely to be any unpleasant surprises. But what that looks like is, so here is sort of sampling from 3 different theories, moving towards the continuum limit. And then this is just sort of a time series of what the topological charge is as the system evolves. You can see here, it mixes very rapidly. But as we move further along, the mixing slows down very quickly. And so
if we can measure the topological charge, why not then like start in one topological charge, your Monte Carlo, do it for a bit, and actually don't jump into the other one and try to do them in different topological charges and
right,
sum them
yeah,
up.
good question. Yeah, so you can totally do that. And if you do that and just leave it stuck in one of the topological sectors and then do that separately for each sector, what you'll get is a bunch of samples, or like sort of a bunch of different ensembles, each of which tells you about a conditional distribution, which is like the theory given that the topological charge is that value, that doesn't have enough information in it to recover the full theory. What you still need is the relative weights of the different topological sectors. And the only way to get that is by running it long enough that you observe many of these tunneling events, because those tell you how often, you know, this sector should be represented relative to another one, but you won't know how much q equals 0 there should be instead of q equals 1.
Right.
But you could also compute the evidence for each one, right? Normalizing constant and then not to weight them together.
Yeah, but then that ends up being like a partition function ratio thermodynamic thing. So yeah, I mean, you can do it. It's just sort of another separate computational challenge. Yeah, you're right. There are other ways to approach that.
But I mean, to do that, you have to know where are those, right? You don't know how do you sample different.
We definitely have a catalog of the topological charges, and we have examples of each, right?
I thought they are purely random.
I think you could do something by like, I don't want to get too involved in this. This is a like good class of ideas. But you can definitely do something where like you draw a bunch of configurations from like R uniform, which has really good coverage across a wide range of topological charges, and then try and equilibrate from a bunch of them and see where like each one gets stuck, and then just do that until you have a good representation of all of the sectors. You can do that.
But I think that you are right, that the difficult thing is to compute the relative weight of topological sectors. So to compute an expectation value on a sector of q equal 1 or 2 is very easy.
Mm-hmm.
But what is much more difficult is to know how much more important is q equals 0 than 1. This is, you can compute a ratio of partition functions, is right, but this is also hard.
Yeah.
So the freezing topology has a volume dependence, right?
Mm-hmm.
Is that the volume dependence? It's just the T's out. So.
Yeah. It's
why is it's always around 0? Is there a kind of reason why it's always around 0?
Yeah, I think it's symmetric.
Okay.
Okay, but let's move on. Okay, so you understand generally the sampling problem that we want to solve and the main challenge in it. So let's move on to how we might use machine learning to attack this problem in the sampling problem. Okay, so good. So here's an example of a lattice field theory. So this is the action for phi 4, or an action for a version of discretized phi 4 theory on a lattice. So you have just some scalar value on each site. Here's the lattice action, and then the density is proportional to e to the minus s. And down here, there are some examples of configurations drawn from this theory for some value of the parameters. It doesn't matter. The main thing to take out of this is if you look at this, you say, okay, I have one number on each site on a 2D grid. This looks kind of like monochromatic images. And if you imagine having more numbers on each site, it starts looking like images with colors. Maybe I shouldn't have used a two-color color map for this. Okay, but the analogy is there. So the idea basically is that lattice field configurations look like images. So can we take all of the technology people have been using or developing to do image generation and reappropriate / adapt it to generating lattice gauge fields instead? Okay. So so let's work up through the concepts of one approach. Specifically, we'll be getting up to normalizing flows. So there's a lot of different things that fall under the heading of generative models in machine learning. The one particular approach I want to focus on sort of starts looking like this. And the basic idea is if I have some function that I've parameterized in some neural way, I can transform samples from one distribution and get samples from another distribution. So imagine I have some neural network. All of this diagram means is that I have some function with lots of parameters, and it takes some input here, and it spits out some output here. If I imagine drawing some samples x from a base distribution, so whatever, imagine like a Gaussian, and then I pipe those through this function, I'll get samples from some other distribution, which I'll call the model. So this is just a picture, let's actually do it. So here I've drawn some samples x, I've initialized some random neural network, and I pipe these values, these one-dimensional values, through the network and get these mapped to values instead. And if I keep doing this, I can build up my base distribution, or a histogram of my base distribution. I just took the 1D Gaussian. And on the other end, this distribution, which arises or is induced as a consequence of whatever the parameter values in this neural network I initialized were. And you'll notice this has some sort of crazy non-trivial structure to it. The shape of that can be tuned by adjusting the parameters in the function I piped all this noise through. And so that's sort of the idea. It's like, can we tune this or use this to use this in a useful way? Yeah, so base model, just terminology I'll use repeatedly. Okay, so the idea is, can I, or can we, take draws of Gaussian noise, so imagine, or something like this. Can we take the equivalent of, I just draw independent Gaussian noise on each site, and then can I pipe that through some learned function that gives me field configurations that look like they should be from scalar field theory? And the answer is basically yes, you can do that. The more important question is, given that you can do that, how can you ensure that you get exact results? So I sort of harped on earlier that when we do these Monte Carlo calculations, we're computing path integrals exactly. We're not making any modeling assumptions. We're not making any approximations that we can't control in principle. We're able to get exact results by doing lattice QCD, exact predictions of QCD. So how can we retain that while we are using some black box to generate our configurations? So yeah, okay, let's just do it this way. So what we want are expectations under some target density, and I'll refer to this always as P. And that is sort of like the theory we're interested in. P you could think about as real QCD. What we instead have is samples from some model density. So I'll say phi is drawn from this model density Q. And maybe Q looks a lot like P, but isn't exactly the same. So what we need to guarantee exactness in order to recover exactness while we're using samples from our model density is we have to, or model distribution, is we have to be able to compute the exact model density. So the equivalent of, here is e to the minus s for our theory. There's some equivalent e to the minus s for the model. So if we can do that, we can reweight our expectation values. So this O sub p is the thing we actually want to compute. If you write this out as a statistical expectation, it looks like this. We have our model density and our observable, and the model density provides a weight. I can multiply by 1 to introduce the model density, and then I end up with this ratio of P over Q. So the target versus the model density, and I call this the reweighting factor. So I can look at this last expression, which is the same integral that gives me the thing I want, the expectation I want. And I can say, okay, now this is a reweighted expectation under a different density, under the model density, which I can sample from using my machine learned thing. I can compute that just using Monte Carlo in the same way. So instead of measuring the observable on every configuration, I also measure the reweighting factor and take the expectation of their product. So as long as I have access to the lattice action I want to sample, I can compute P, and I always have that. And as long as I have access to the model density, I can compute P over Q and do these sort of reweighted expectations. So that's the structure I need. So diagrammatically, here's a picture of what this looks like. I have some base distribution R. I pipe it through my function f, and this gives me this blue histogram Q, which looks like P, but isn't exactly the same. I have some reweighting factors like this. And so this is sort of the I divided these two histograms. And here it's sort of P over Q. This line is at 1. If all of the reweighting factors are 1, it means that your model is exactly the same as your target. So you wouldn't expect, this factor becomes trivial and you just recover the same expectation. Once you get any deviations around that line, you start losing model quality. You start introducing extra variance due to having to include these reweighting factors. And there's this common quantity we like to compute called the ESS, which quantifies the increase in variance due to reweighting. So a perfect ESS is 1, means it doesn't increase the variance at all. A very bad ESS is 0, it's 1 over infinity, completely blows up the variance, and so you have a perfectly bad model.
Question. So does that mean we are transferring the part which is not exact to this W?
Yes.
Okay.
Yeah, but introducing the W gives you back the expectation you want exactly.
Okay. So the main difficulty is how we have a good W.
Yeah. So the challenge then is, can you make a model where the reweighting factors are like close enough around a 1 that you don't completely blow up every expectation value you'd like to compute? Okay, so the construction that satisfies this property that we want, that we can compute the model density, is something referred to as a normalizing flow. So I won't dwell on this slide too long, but yeah, so the idea is already kind of what you've seen. We have some simple base distribution. We know how to compute the density of that base distribution. And then we have some function which gets us from the base distribution to the model distribution. So for a flow, it's not just some function. It's not just some formless blob of neurons. Instead, it's something parameterized by neural networks, but with more structure. The neural networks sort of sandboxed in a way that lets us take advantage of their black box nature, or avoid the black boxes causing any problems. A flow is a diffeomorphism, usually, which means that it's an invertible function. And usually we construct them so that the Jacobian determinant is tractable to compute. And given that you can compute the Jacobian determinant, which is this factor here, and the base density there, you can compute the density under the model given a construction like this. And this gives us everything we want. So then the question is, how can you construct, this is an abstract specification. How can you construct one of these concretely?
Wait, can I ask?
Yes.
What flow come from? Why is it called flow?
Can I show you the next slide?
Okay.
Yeah. Okay. So one example of a thing, one way you can construct a flow is this idea of doing neural ODEs, or a continuous normalizing flow. So the idea there is to sample, what I'll do is I'll integrate some differential equation like this. So I promote my fields to, okay, let's say I draw a value of my fields from my base distribution, and I say this is the value of the field at time t equals 0. Then what I'll do is I'll write down this ODE, which describes its evolution in some fictitious time direction. And the force, which is aligned with, this is a vector in all of the sites. The force, also a vector in all of the sites. This is some learned function. It can be whatever I want. It can be a function of time. And so as you integrate along this trajectory, you can look at what happens to the distribution defined by this. So like same idea as before. I start off with a Gaussian distribution, and then I integrate for each sample from this along I randomly initialize some neural network to be the force field. And you can see that the distribution slowly evolves. And so sort of the picture in your head is that you have sort of probability mass flowing around as you evolve things using this function. So the idea here is, so because this has learned parameters in it, the shape of this output, again, is something learned and tunable. And I said we needed to be able to compute the density. In the case of a neural ODE, you do that by just integrating the second integral alongside everything else, where it's just sort of the divergence of this function, which you can generally compute using AutoGrad, or you can make it even more structured in a way that makes it easier to compute than that.
So every time I only construct one f, and I repeat that several times to have longer flow time. Is that how that works? Or I increase the number of layers to increase the time of.
Yeah, I mean, so we're not thinking about layers yet. So just think about this as actually an ODE.
Okay.
But yeah, I mean, so this f is a function of the field at that time, and also the time in general. And then you can choose how far out you integrate it to, but like usually you integrate to like 1. just because you have to pick a number.
Okay, so do you need, for each time you need to train for an F?
Yeah, these are hard to train.
Okay.
Yeah, and so I was getting to like, these are computationally expensive. They're usually very expressive. They're very powerful in general, but just training them is generally hard because you have to numerically integrate this, and backpropagating through like a numerical integration is kind of hard. There's other methods to do it, but these are sort of impractical if you care about doing things on billions of degrees of freedom. So instead, most of what we've been experimenting with are what you can think about as a sort of discretized version of an ODE flow. So if you think about numerically integrating, you're going to have to do that in some number of steps. And so it's in practice, it's already sort of discretized. And here, this is sort of making that structure more explicit in what's usually called coupling layers. So the idea, maybe said a different way, is we're going to transform from our base distribution to our model distribution using a stack of many simple subtransformations. And we'll exploit a nice trick called variable partitioning, where the idea is, so imagine I have my field at some stage along this sequence of transformations. And I split it into two different subsets, maybe by checkerboarding. And I call them the active variables and the frozen variables. So what I can do is I say maybe this layer, this transformation in my stack of transformations won't update these frozen variables at all. It performs the identity operation on these. And these active variables, it will update using only information about the frozen variables. And each one of these gets updated independently. If you do this, with sort of minor other restrictions, if you do this, you end up with something that's both explicitly invertible, because you can always, I won't explain it. It's explicitly invertible, and also you end up with a triangular Jacobian, which means you can compute the determinant of the Jacobian very inexpensively. Great. So then, finally, last concept on how flows work in general, how you might build them, is this idea of self-training. So one thing you might worry about is if we're trying to do a sampling problem that's expensive and trying to train something to do that more efficiently, you need to get the training data from somewhere. And so you end up with sort of maybe a circular problem. And fortunately, we don't have this circular problem because we can have the models train themselves. We don't really need external training data. The way we do that is by minimizing this thing called the reverse KL divergence. So you've probably heard of the KL divergence if you've been to enough machine learning talks. It's just this integral here, log of Q over P, where those are the two densities, evaluated under the model distribution. This quantity is 0 when the two distributions agree exactly, and it's greater than 0 when there's any disagreement between them. Let's see. So you can use this as a training objective with, so because of that, this makes a nice training objective. So if you minimize the KL divergence, you'll get, you'll push towards the two distributions agreeing with each other. You guys want to close that? Yeah, sorry, that's kind of distracting. Yeah, and then that's another advantage here is that Q and P can both be unnormalized. This only changes the thing up to a constant, and so it won't affect the minimization problem. But most importantly, you'll note that this is an expectation with regards to Q, or under Q, the model density, which means that we only need model samples to evaluate this, and we only need model samples to train. So as long as it's inexpensive to evaluate the model, to sample from the model, you can generate as much training data as you want. And so if you sort of imagine, or not imagine, if you apply this training procedure, you end up seeing something like this, where over time your model quality is measured by something like the ESS will increase, all without generating data from any other sampling algorithm.
Wait, but if I train like that, I'm sorry, you haven't told us how to compute the W yet, right?
No, I kind of have. Yeah, so this is sort of how you compute the W. Is like I just need to be able to compute the determinant of the Jacobian in my transformation. I need to be able to compute the base density, and then I can, for any given sample, I can compute Q. I can always compute P. That's just some function that eats a field and gives me a number, and I have it written down somewhere.
P can compute?
I can always compute P.
Or is
defines-
No, because you don't know
it
Z.
e to the minus
Is it?
action?
Yeah, P is e to the minus
E to
action.
the minus action. But the
But
action.
Given a
Divided by Z.
configuration,
Given-
you can evaluate P of that configuration.
But don't I need the partition?
Z cancels out.
No, because both,
Yeah, yeah.
both,
You
both
do-
distributions don't need to have the same partition function.
No, yeah,
They don't need to be normalized.
yeah. So you're right. You caught something that I was trying to glaze over. Yeah. So you need the normalized reweighting factors in practice, but usually, yeah, you're right. We only have e to the minus s. We don't have p. Most often we have a normalized version of q, but the overall thing is not normalized. But what you can do is just say, okay, I know the expectation of w should be 1. I know these are off by some overall constant, which is z, and then you just normalize them. Technically, this gives you a statistical bias, but it goes away as your sample size increases.
Okay.
Yeah.
Okay.
Okay, are there any more questions on sort of the general concepts part of this? Good. Okay, what have we been doing for lattice QCD? So we've written a lot of papers, that's the main thing. So kind of what we've been doing is we've been working up through increasingly complicated problems. So we started off, okay, I should say, Tasian friends started off without me and I hopped on right after on scalar field theories, and then worked up through doing gauge theories, adding in fermions, and then more recently been testing applications to small, easy versions of QCD, trying to work up towards demonstrating a computational advantage in some sort of realistic setting. So along the way, we've had some cool results. So one of them from this U1 paper has led to this often imitated plot here, where we showed that using flow-based samplers, we can sort of resolve this topological freezing problem, at least in these certain parameter regimes of 2D U1 gauge theory. And so just to explain this plot, this is a topological charge history, like I showed earlier. The blue line here is how it evolves under HMC. The black line, which moves a little faster, is how it evolves under a different algorithm called heat path that you've maybe heard of. And then the orange fuzz in the background is using a sampler constructed with a flow. And the fuzz in the background is telling you that this is moving enormously faster than these traditional algorithms can. And then, yeah.
Wait, did you guys know that was gonna happen beforehand? Like I don't remember. There was no reason for using machine learning to solve the Q problem, right?
You can kind of So I guess what I didn't mention is, yeah. Okay. So in constructing the sampler, it's not necessarily doing reweighting. Instead, you're using it to construct a Markov chain. And the way that works is you sort of propose the sample and then you accept or reject based on the ratio of the reweighting factors. Mm-hmm. And so it's sort of just, you can think about it as a different way of doing the reweighting, but it gives you like a Markov chain version of it that you can compare with other algorithms. If you think about it that way, every sample you draw from a flow model is completely independent of the previous sample. So as long as you get an acceptance when you're constructing a Markov chain like this, it completely scrambles the state. So this picture I drew earlier where you're sort of wandering around on a potential surface doesn't apply. It's more like you sort of say, I want to go here, can I? And then just pick points completely at random on the field space. And then it's just, you need to be able to have those accepted. But once you have those accepted with some frequency, you sort of move around arbitrarily quickly.
So it's not a time averaging process or something?
You can think about it as a time averaging process in this case, but it's there's no sense of motion. It just sort of teleports around.
Wait, the acceptance, what was the acceptance criterion again?
Oh, it's like you compute the ratio of like the reweighting factors of the proposed configuration with the old configuration, and then draw a number between 0 and 1, and if it's less, then you accept.
So it's
a version of Metropolis.
Right, there is still an autocorrelation, it's just that the correlation that you obtain because your proposal depends on your previous step, that doesn't appear.
Yeah,
because the proposal doesn't depend on the previous step, it's
Yeah,
just the acceptance that
right.
depends.
Yeah, so if you think about generating a Markov chain this way, I think another way to say what you just said is that the only source of autocorrelations is rejections.
Right.
Yeah. Good question. Okay. Yeah, so what are some highlights of things we've needed to do along the way? Okay, so I think I'm gonna maybe not spend too much time on this. So usually machine learning operates on real valued quantities, but gauge theories, the degrees of freedom often live on compact manifolds, so that required developing some novel technology to treat. Sort of a lesson learned is that training or increasing model size, at least in most of these settings, tend to provide sort of diminishing returns. We don't have the same situation with language models where we can solve our problem just by going to larger scales, or at least not yet. So instead, what we found is important to get improvements in our model quality and thus our sampler efficiency is incorporating physics to make more qualitative algorithmic improvements. So here's two examples. Maybe I'll explain this one because I think it's a little bit more interesting. This is models for the same scalar field theory, so just some set of parameters. Here I'm varying the number of layers, so I'm making the model bigger. And you can see that this blue line increases but sort of flattens out. This orange line, which is a different class of architectures, increases but flattens out. The difference between these two architecture classes is this one uses an independent Gaussian prior on each site, and this one uses a free field theory with a learned pole mass instead as the base distribution. And you can see that that change just by itself, which is like simple and computationally inexpensive to sample from, to add in, means that the smallest model with that base distribution is better than any model given a more naive, less physics-informed base distribution.
What is it, learned pole mass? What do you mean by that?
Pole mass.
Isn't that what you said?
Yeah, that is what I said. I'm trying to think of how to. It's basically like the Fourier transform, and then multiply on like 1 over m squared or something like that onto the zero momentum mode. That's all I meant. I wasn't trying to be fancy. Yeah. Good. Or we're physicists. We like to think about things in terms of symmetries, and so incorporating symmetries into the models, as it turns out, has been sort of the most powerful tool we have. So here's an example in mode structure. Well, let's just skip ahead. Yeah.
Wait, but then like. What is the lesson there for something like QCD where like the masses are like have nothing to do with the masses of states?
Yeah, I mean this you can't do this for
Okay, so
this is just an example where it's like
where maybe there might be something, but it's not obvious how that's connected.
Yeah. So like this technique does not directly translate to QCD. This is just like, okay, we looked at this field theory, we said what might be a sensible thing to do, and look, it worked much better. That's like the full lesson learned from that one.
Cool.
Good. Okay, so we want to incorporate symmetries. So why exactly though might we want to do that? So these two pictures are sort of descriptions of or sketches of how you can think about continuous symmetry. So the density here is sort of the density over field configurations. And so let's say our tree distribution looks like this. So we have some invariant direction, which is physics. This is where all of the interesting structure lives. Then we have some direction, which is just the symmetry orbit. And the density is flat along that direction. So that's just what it means for, a symmetry of your quantum field theory corresponds to a flat direction in your probability density in the sort of corresponding sampling problem. If you imagine trying to approximate this with some arbitrary parameterization of your density, which doesn't encode the symmetry exactly, you can imagine maybe the best you can do given some finite amount of training might look like this. So it looks basically like this, but you'll notice that it's sort of squiggly along this direction that should be exactly flat. And this squiggliness will sort of hurt you. This will result in some loss of model quality. And if you can build in a flat direction so that you automatically get that correct, this can really increase the quality of your models, especially when you have some really high dimensional continuous symmetry group like a gauge symmetry on a lattice. Okay, so how do we incorporate these into flow models in general? So the idea is there's sort of a general approach. The idea is you have some invariant base distribution. So that notationally that means this. If you rotate your configuration, it has the same density under the base. And we have some equivariant flow, which means that if I have some symmetry transformation, it commutes with the action of the flow. And so then combining those, you think about, okay, I apply some symmetry, it commutes back through the flow, it runs into the base distribution and disappears. So what does this look like? let's do an example, translation symmetry. So convolutions convolutions are a linear operation. They commute with translations. So they're translation equivariant, you would say. So what a convolution looks like, as usually defined in machine learning, is we're going to have some 3x3 kernel, and we're going to scan it over this image here, and that will produce literally the convolution of those two things. But you can think about it as sort of smearing this image with these learned weights. So what that looks like is this. So we apply the convolution. You see that information is sort of smudged out. The action of this is sort of a function of what the kernel weights are. And so that's what you get. Now imagine we roll this image down sort of halfway using periodic boundary conditions. So the bottom rolls off to the top. So this is the translation. That gives us this picture. So now you can imagine applying the same convolution to that one, and you'll get this image. And you can roll it back, and you get back to the same image. So that's all I mean by the operation commutes with the action of the flow. Or in this case, the action of the convolution. I can get from here to here, either by applying a convolution or by translating, applying it, and untranslating. Okay, so kind of returning to the ODE flow example, how might I build equivariance into a flow in general? So this, like many great ideas, was something Lucia figured out a long time ago. If you set up a gradient flow with respect to some potential, and that potential, so I said before we have some learned force field. Imagine instead I define that force field as the gradient of some scalar function. Still learned, but just a different way of parameterizing it. And suppose that potential is invariant with respect to some symmetry. Specifically a symmetry that acts multiplicatively and I think maybe linearly. So if the potential is invariant, the gradient, which I use to define the force, will be equivariant. The symmetry operation pops out. And that just means that the dynamics are sort of insensitive to having the rotation because the symmetry transformation just sort of factorizes out on both sides. You can define a gauge theory version of this just by taking some gauge invariant potential. So this is just the gauge version of that. And so if I take this as tilde, and I take this operation here called a Lie derivative, I get some SU3 valued equivariant force. I have some differential equation, and I have all that. What this equation means, if you're used to lattice things, is this is just doing Wilson flow, except for instead of having the Wilson action, you have some learned S tilde thing. So this is sort of a generic way of constructing ODE flows for lattice gauge theories. As in the, like I said before, ODE flows are complicated and expensive to deal with. So there's sort of a large school of different versions of doing discretized flows instead, coupling layer flows, like I mentioned earlier. Here's some references, but I think technical details aren't worth getting into. Okay, so this is sort of the important highlights of what we've been doing. So sort of the state of things now is as we're trying to get up towards computational advantage in large scale, realistic scale problems, the two directions we've been exploring, pushing in, are one, we need to have better models in QCD than we have now. We can't do direct sampling at parameters that you would want to do a state-of-the-art calculation at. The second one, though, is are there different algorithmic use cases for flows than just completely replacing the current entire sampling pipeline? And the answer is yes, you can do this. And this is sort of what my last section is about. Okay, so this is the picture we've been thinking about so far. We have some really simple base, like a Haar uniform distribution. We flow F to get some model, and we reweight to a target. But we chose to use a really simple distribution here. We chose, in all the examples I was talking about, to use some trivial distribution like a uniform or like a Gaussian on each site. We can choose whatever base distribution we want, as long as we can sample from it and compute its density. So the basic idea here is don't flow as far. And instead of using some trivial distribution as our base, instead use some maybe slightly easier to sample field theory. So you can imagine versions of this that are try to make a flow from pure gauge theory to a theory with fermions. Or even simpler, you can imagine trying to make a flow from some version of QCD at easier parameters to QCD at slightly harder parameters, and try and exploit that sort of thing for computational advantages. So I'm gonna run through two quick applications we've been exploring. One of them is on this sort of sampling problem still, ways to ways to try and resolve topological freezing by simultaneously sampling nearby theories with replica exchange. We have this lattice proceedings out about it. The other application is using using flows to generate multiple correlated ensembles to reduce variance when you're computing derivative observables. Okay, and there's a paper out about that as well. Good. Skip over that. Okay, so first thing, application one. So maybe you've heard of the replica exchange or parallel tempering algorithm. The idea there is you have a few different closely related sampling problems on the same degrees of freedom that you'd like to sample simultaneously. So let's say it's two different theories, maybe QCD at one lattice spacing and then QCD at another. One way you can sample that is by simultaneously alongside each other, independently sampling each one of those. So you have these sort of streams Markov chains evolving in parallel. And occasionally you can try and swap the configurations between different streams. And so the unflowed version of this has been known for a long time. The issue is that if the theories are not very similar, these swaps are almost never accepted, and then you might as well have not done anything at all. The idea, as originally introduced by these guys, is to use a flow as sort of a bridge between these theories to make swaps more likely to accept. And so what you do is basically, instead of just proposing a swap, you first flow this configuration towards that chain, this one inversely back up towards that chain, and then there's a modified version of the swap probability. The idea of why you might expect this to work is basically just that if you swap into, if you imagine you're in this hard theory, like this drawing I made before where the two modes are very separated, if the state of this system can sort of pop over into an easier theory where the modes are less separated and evolve there for a while, it's easier to sort of get from one mode to the next, and then eventually get swapped back in to sample in the other mode. And so that's sort of the picture of why you would expect this kind of thing to work in a mode freezing situation. So all we need to do is introduce theories which are less well separated in the modes. So one thing you can do is, so topological freezing sets in really rapidly, as I showed these exact plots before. What you can do is set up a flow between these three theories. So one flow bridges these two, train another to bridge these two, and running that exact algorithm I did before, you can see we get quite an improvement in the mixing rate. Although in this case, if you're careful about the statistics, if you only cared about sampling this theory, this isn't quite a computational advantage yet. You can also consider a different version of this.
Why? What do you
show there?
Yeah, so the autocorrelation time in this stream is 70, but if you imagine you had to run these as like sort of nuisance, you're running 3 times as much heat path. And so you sort of pay a factor of 3, and then you're not really beating that one yet, is the idea.
So the autocorrelation of the top is 225?
Yeah.
No, this cannot be right. I mean, the number of the left or the below is much more correlated than the ones on the top. I mean, if you have a short Monte Carlo time, you might have a huge error. What is the error in these autocorrelation times? Let me make a concrete question.
Good question. I don't think we computed a rigorous error on these, but I have to double check.
What I would say,
yeah,
from a general point of view, yeah. I mean, if you look at the number of times that you cross the average, that the average topological charge is 0, clearly the plots on down, okay, are much more correlated than one of the other. The only problem is that the error below can be at 300%. because you don't have enough jumps. I mean, of course, I mean, in the limit, imagine that you are completely stuck at q equals 0, that the correlation time will be very good, but it is wrong.
Yeah, but
Yeah.
a lot more numbers went into making these numbers than are plotted here.
No, but I only want to support your thing. I think that the numbers on the top where you swap the replicas is much better than the one. Despite of whatever you have done to compute this autocorrelation times tells you. I mean, clearly the swapping works.
Yeah, right.
I want to say that you are doing good. I mean,
how did I not hear that?
You should not pay attention to these numbers because probably they have a huge error.
Yeah. Okay. Thanks. So, good. Okay, so another thing you can do is rather than going between different theories, which each individually might be physically interesting, you can instead introduce sort of extra nuisance theories just put in to accelerate mixing in one sort of fiducial target stream. And one strategy already explored without flows by various people is this thing called parallel tempering on boundary conditions, where the idea is, so opening boundary conditions is known to accelerate topological mixing, but introduces its own problems. So what you can do instead is sort of open part of the boundaries in these sort of fake theories and then slowly anneal it away and then sample between all of these. And so the idea is the topological charge will mix much more quickly in these theories with a defect and much more slowly in the target stream, but the target stream will be accelerated by mixing with these. So this has some advantages, specifically that the flow only needs to operate on a subvolume, so you're not subject to any sort of recursive dimensionality, and the price of a computational cost of executing the flow remains small. We tried it, but it's not quite advantageous yet. Okay, finally, I think I'll probably skip the explanation of the numerics part, but I wanted to get across the idea for this last demonstration before I closed. So the idea here is, so imagine I have some ensemble of gauge configurations drawn from my theory that I'll label R. So each of these boxes is some field configuration. And then suppose I have some flow F, which sort of approximately bridges between R, my base, and a target theory P. If I apply that function separately to each one of the field configurations in this ensemble, I get a second ensemble distributed per theory Q, my model distribution. And these two ensembles are correlated. They're not independent, and this can be useful. So specifically, this can be useful for taking noise cancellation when you compute differences of things. So suppose I'm interested in computing the difference in the expectation of some observable in theory P versus theory R. You could rewrite that, assuming you have such a flow, as sort of the reweighted expectation under your model minus the one under your base to begin with. You can sort of jam all of that into one expectation, writing it this way, which I think kind of makes obvious that you are computing something where you'll get correlated noise cancellation between these two terms, is all I'm getting at. And so what this is specifically useful for is if you want to compute derivatives with regards to things like an expectation with regards to action parameters. So examples of things you can use this for are things like if you want to better constrain extrapolations to the chiral or continuum limit, you could compute the derivative of some observable with respect to whatever action parameter tunes towards those. Or maybe more interestingly, there's a class of methods that are often used in lattice calculations called based on the Feynman-Hellman theorem, where you add some perturbing parameter to your action, which lets you insert an operator into a hadronic state by just computing the derivative of the energy of that state with respect to the parameter. So this is used to do things like compute like the nucleon pion sigma term, or in some cases, the gluon momentum fraction of some hadron. Okay, and so we went ahead and tried this approach, and basically I'll skip to the punchline, which is that if you use this method of using flows to take finite differences, you can get a 5 times variance reduction in this example of computing a momentum fraction versus just the exact method. Or the more common approach of using independent ensembles, you can get a 7 times variance reduction. There's a good argument to be made that have to refer to our paper for, that this is actually, in this example, a true computational advantage in this calculation. But there's a little bit of complications there that I won't get into. And we tried it on a bunch of other stuff, and it also worked there. Good. Okay, so just to close, so we are working on it. We still think flows are a really promising approach to configuration generation, although maybe I should remove new now that we've been working on it for so long. Important things to note, take away from this, is that we can do provably exact theoretical physics using machine learning. We don't have these irreducible black box uncertainties. There's a way to do that. The samplers you can construct have different properties from traditional sampling algorithms that might be useful in resolving problems like topological freezing. We're working up to QCD, but a lot of work remains to be done. There's a lot of space in the space of architectures and training schemes to explore, a lot of engineering required to run things at larger scales, and further analysis of what can or should work has been proving to be very helpful. And finally, I hope in the last bit, even though I rushed through it, I convinced you that even if we can't quite do full generative modeling of the QCD path integral yet, there's opportunities to do things useful in the near future. So that's all I have. Thanks for your attention. Sorry to go over.
Sorry for naive question. So every time before you actually perform the apply the algorithm, is there does it always give you a feeling that the machine learning is always faster, except for that you use GPU, which is usually fast, take advantage of that. Except for that factor, will the machine learning always be faster?
It doesn't always feel faster.
Okay.
Frequently, heat path feels a lot faster. It sort of depends. Yeah, I mean, so the issue is like a lot of the time evaluating these flows is really expensive, and this is something that you can optimize. Like my ballpark guess is there's probably a factor of 10 to 100 versus the implementations we've been doing. But a lot of the existing algorithms have been optimized for like 20 or 30 years, and I think the place where you can win is when you have these mode freezing problems. Like this is where there's an opportunity to do something, because there isn't really a way to get around that with these traditional algorithms. And if you keep pushing towards the continuum limit with HMC, you're just going to run into an exponential wall. And so there, it doesn't really necessarily matter how fast the execution is if you are beating it on statistical efficiency by many orders of magnitude.
I think I get the gist of like why you want to apply these methods for like field generation. It wasn't really clear to me what the advantage is for like for observables. I mean, the last thing that in particular, like it seems like you're generating a whole, like for example, like the sigma term example, right? I can imagine some cases where, of course, like if you want to incorporate, say, QED, you want to look at differences, QED effects, and you want to have like QCD, the QC Lagrangian with and without QED effects. Maybe you want to apply something like this, but something for like the sigma term, instead of going the straight method, which is all you end up evaluating correlation functions. This seems like a much more computationally costly. This seems like way too big of a hammer for such a small nail. So maybe I'm missing something. Like why?
Yeah, I mean, so one of the things going on is there's sort of a lot of different hammers, and different ones are appropriate for different nails. So, like a lot of the time, you'll just compute the derivative analytically, and then you like have some extra correlation function you compute that has maybe a few more terms in it. You can get a statistically equivalent thing by just doing like reweighting only like a tiny epsilon away. And so there's sort of like an exact version of computing derivative observables, and for things like GA or whatever, this has worked really well. For other things, like a lot of the more like the gluon momentum fraction calculation we were trying to improve, did this approach of like you generate 7 ensembles at really wide lambda, and then you use those to try and compute the derivative at lambda equals 0. And you're exploiting the bias variance trade-off in some sense when you do that, to take some really noisy observable and accept that you have to do some modeling to try and control your errors at, to get a huge variance reduction over if you did the exact thing. And so the idea here is, this isn't going to be universally better than either one of those methods. Like the float thing will give you some bias versus the exact method. It'll give you less bias, but less potential for variance trade-off than doing separate independent ensembles. And so it's sort of, you know, a different hammer you could consider.
But do these the different topological charges you emphasize that, do they really matter for the observables?
Yes. Yeah, like you can get totally the wrong answer if you don't account for it correctly. Although some people would argue with me on that one.
Right, and I heard also that they would argue with you, especially in the A=0 limit. Is that true or not?
Ooh, yeah. I mean, so, okay, there's a statement often made that you don't have to worry about topological freezing because all of the issues, or like all of the differences between different topological sectors are like a finite volume effect. I believed that for a while, but I've recently thought about it in terms of I don't see how you can do that and still have a strong CP problem. And I believe that there's a strong CP problem more than I believe that argument. And I can kind of explain that better, but maybe not in front of a room full of people.
I think that the problem is, first of all, is if you lose ergodicity, then conceptually you might have some problems. But it is true that in principle, you can do simulations at fixed topological sector. And now, as long as you compute local correlators, the effect is a finite volume effect. But the price that you pay is that this finite volume effect is power-like instead of exponentially suppressed. So in QCD, if you sample all topological sectors, finite volume effects are exponential in the pi of mass, and they are small, okay? The finite volume effects associated with topology freezing are 1 over L to the 4. And why do you want to pay this price of finite volume effect? Then there are other issues that, depending on the kind of physics that you try to do, where this can mess up. For example, for your cases, okay, that you are basically interested on a finite volume effect that is physical, if it is giving you some scattering amplitude. If you have a finite volume effect that depends on the topological sector, then you are screwed. So there are 4 cases that being stuck in a topological sector is an issue. And one comment about this last application that you want to measure derivatives. Mm-hmm. You can construct, at least for a big class of field theories, and I don't know for QCD, okay, you can construct the transformation exactly. No training, nothing. And this, this is what we tried to talk the other day. I mean, basically, if you use the HMC as a flow, okay, it can build the transformation that makes you compute all the parameter dependence in these observables to any order in lambda that you want. Okay, so you have an exact solution of this problem with where the ESS is equal to 1 by definition. Okay. And that, in fact, when you apply it for some toy models, lambda phi to the 4 in 4 dimensions, you can compute derivative with respect to lambda 100 times. I mean, an exponential in the volume more efficient, not a factor of 5.
Is this the stochastic perturbation theory thing you were explaining? Yeah. Okay. Good. Thanks.
So I guess one of the issues with the flows is the training as a function of dimensionality, and it goes exponentially down, or training time goes exponentially up, I guess. You didn't say much about that.
Training time doesn't go exponentially.
Well, maybe not exponentially, but anyway, very steep. So, I mean, can you say a little bit more? I mean, can you actually scale this to what modern LQCD calculations are?
Not right now. So a few comments on training cost. So all of the models we do, or all of our model architectures we've done in the past couple of years, you can apply on different volumes. So the models are sort of defined in a volume independent way, which lets you do training on small volumes where the cost really isn't quite so much a factor. And that actually ends up transferring even without retraining really well. Like it frequently isn't worth training on the larger volumes at all. So that sort of transfer learning strategy seems to work even better than we expected it to. And given that, I'm less worried about training costs than I had been previously. There is still separately, when you're evaluating these things, this sort of issue of the ESS degrading exponentially as you increase the volume. It's a form of cursive dimensionality. And this is a difficult obstacle. It means that if you want to scale up to some large volume, you effectively need like a high precision model. Because if you start off with some model that's an ESS of 0.99 on whatever small volume, like 4 to the 4th, and then you have to go up to 64 to the 4th, you're paying, how does math work? is that like a factor of 16 to the fourth? So like ESF, 0.99 to 16 to the fourth is a small number. So you end up needing to be able to do high precision models if you want to do these sort of full generative modeling
The
scenarios.
16 to the 4 goes in the exponent.
Yes. Yeah, so it's 0.99 to the 16 to the fourth. And so you end up needing a few extra nines if you want to have a finite ESS on larger volumes.
But even this strategy, I don't think that this would be, I mean, there is a problem there, that is that if you try in a small volume, 8 to the 4, you have finite volume effects. So a 64 to the 4 lattice is not just the same as a 8 to the 4 lattice copied many times. Okay? Then this difference, this finite volume effect, this difference will kill you.
Yeah,
This thing.
Totally expected that, and it ends up being way less of a problem than you think.
Have you scaled this to 64 to the 4?
I mean, we've scaled, 4 to the 4th up to like, 16 to the 4th or that kind of thing, and seen basically, you can try training on it, or you can try transferring up to the target volume. And
If you retrain, it's a different thing, but if you don't want to retrain on the large volume, this is a straight exponential.
What I'm saying is, it is a straight exponential. What I'm saying is retraining on the larger volume, you'd expect for it to correct for the finite volume effects that you didn't learn right on the smaller volume, but it ends up not really mattering. I don't know why. And also this could be a function of like how aggressive the fermion parameters are, like maybe once it becomes more non-local. Yeah, but it's been sort of mattering less than I expected it to by a lot.
Do you test observables that are volume dependent after the fact when you do this?
Good question. So I mean, if we compute the reweighted observables, they're guaranteed to be right. I haven't thought about looking at the model distribution observables, or I guess we have, but I don't know that I've ever found any insight in doing that. But that's interesting.
I mean, just talking, but if you train, for example, in an 8 to the 4 lattice, it is absolutely impossible that this model knows how much is any correlator at 9 lattice spacings. Absolutely impossible.
Yeah. So you think that, but here's a different way of looking at it. So these flows defined as in a volume independent way.
They are invariant under translations. I understand.
Yeah, but also like you can take the same set of parameters and then apply them on a different volume. So you get this like direct volume transfer thing.
Sure.
So you can think about that as some sort of like flow model, or you can think about it as some action defined exactly the way an action like the Wilson action would be in terms of some kernel that you run over the whole lattice. And it happens to have weird parameters in it, and it also happens to have a built-in sampler. And if you think about it that way, it's like, okay, like we know with the Wilson action, given that, we can apply that and sample it on different volumes, and we know we get the right physics on different volumes. And so maybe the correct picture is that with these flow models, you get the correct physics on different volumes just by it's just some different parameters applied on different volumes.
But okay.
That doesn't sound spooky to you?
Oh, it does. Yeah.
Okay.
Yeah, I don't understand this part. But
Are there known practical difficulties for implementing QCD? Anything special?
I mean, it's just sort of non-practical difficulties. I don't think there's anything necessarily special about QCD. It's just sort of got all of the complications you might think about. So you technically have like a non-local action because of the fermions, and that's sort of painful to deal with, or not painful to deal with, but just sort of difficult to model versus something with a fully local action, and also it's just very high dimensional.
Can I ask, what do you mean by this theoretical guarantees statement? In the following sense, we know that the reverse KL has this mode not covering issue, right? So in other words, there's a mode out there that you haven't discovered, you'll never know its existence, right? Mm-hmm. So in that sense, I'm not sure what theoretical guarantees you have, right?
Mm-hmm. Yeah. I mean, if you don't have, okay, so the sense in which you have asymptotic guarantees is asymptotic, and asymptotic is never, it doesn't always survive contact with reality. And if you are missing an entire mode of the theory, then you will have an effective loss of ergodicity the same way you always will, and you'll get your expectation values wrong. And the only way to not have that happen is by being careful. And we've been sampling QCD for like a really long time, and we kind of know what sort of mode structures to expect from it at this point. And the main one is the topological mode structure, unless you're looking at the, on the other side of the thermodynamic transition when there's also a separate thing. And we know that with the topological mode structure, at least all of the models we've been experimenting with have had no issue with mode collapse.
In other words, you found all the modes.
Yeah, I mean, like we seem to have good
your
coverage.
exploration technique.
Or it's just, it's just the standard reverse KL thing doesn't seem to cause mode collapse with all the architecture.
Because there are other papers like spin glasses where everybody claimed this doesn't work at all because it misses sitting on modes and stuff like that. Yeah, I mean, like modes are in general hard, and it's kind of lucky that we haven't had problems in this case.
Okay, there's no other questions. Yeah, thanks very much then.